up to the nervous tissue and make the contractions. So when you shine light, if you have a probe that goes through the esophagus and you're trying to scan around, the source of vector separation is going to depend on how you have it. You can cut only through the epithelium, or you can cut through many different tissues, and then you have to think about what exactly is it that you're trying to see. And of course there's blood, and blood itself, of course, the hemoglobin is a very strong absorber of light, and we'll talk about that momentarily. But don't forget that light also scatters, because the red blood cells look like donuts. So they themselves are scatterers. Okay. So basically, bottom line is the tissue is extremely heterogeneous, and it's in fact so heterogeneous that we're getting a headache inside. We cannot solve it exactly, but approximately, if we look at it carefully, we can maybe be able to isolate what are some very preponderant tissue structures that contribute a lot to the scattering, like too much mitochondria, too much cartilage, or whatever. So it could be intercellular or extracellular. Now, the other aspect of it is absorption, because you could be able to tell a tumor from normal tissue because of increased cellularity or packing fraction, but it could also be because the tumor has more blood vessels and bigger volume fraction of blood, therefore it absorbs more. And so the second piece of information after scattering is absorption. And so this is a graph that shows the probability of absorption of light. So if you can imagine a cuvette and you fill it up with blood, and the cuvette is a centimeter long, it's the probability for per unit centimeter of path length that at this particular, there will be a certain amount of absorption. And the absorption is I equals I naught e to the minus e whatever c d over naught. So then this particular thing is the absorbance is a measure of this. And notice that this is a log scale. So if you are at 500, where you're here, you're up here. But if you go to 600, you're down here. So you've gone down by a factor of 100. By moving 100 nanometers, you've reduced absorption by a factor of 100. And then it stays low all the way to above 1,000 nanometers, which is beyond what the eye can see. And then water starts picking up. Water has resonances, and you can see them. But basically, eventually, it becomes comparable to what blood was at lower wavelength. So you have this window between 600 and maybe 1200-ish, where it's called the optical window or the diagnostic window, where light gets absorbed less, and so that's what gives us the opportunity to see deeper in tissue. Otherwise, we would only be measuring surfaces. So most of this class is focused on what happens within this particular optical window. Now, some tissues may have additional absorbers, like skin could have melanin, the bile duct could have bile. There's other things that could happen, but for the most part, we're dealing with primarily oxyhemoglobin, and if there's lots of water, we may care about water too. So now, if we want to look at deeper in tissue, the tumor, if it's deeper, we want to increase the source of vector separation so that the banana will taste deeper. Imagine, you can see that it will not completely evade the skin effects, because no matter what you do, the light has to enter and exit through the skin. But the bigger the separation, the bigger fraction of this banana-shaped volume is going to spend deeper, and therefore you're going to capture more of what's happening below. But you pay a price for it too, because the deeper it is, the fatter the banana, so you're averaging more signal. So you can imagine if you're only capturing a slice of a tumor, and you have a big banana that captures a lot of other stuff, the signal from the tumor will be diluted. So it's kind of a compromise between big versus small. So you don't want it to be too big, because then you will capture it, but you will also dilute it, and that's the issue of sensitivity. It's called, what is it called? Volume averaging, or partial volume effect in imaging terms. And then specificity can also matter, because if it's a highly heterogeneous tissue, like for example in the breast you have cysts, you could have a tumor, you could have normal tissue. If it's highly spatially heterogeneous, if you have the big bananas will average all the signal out, and that reduces the specificity, because you can no longer tell if it's a cyst or a tumor or normal tissue. So sensitivity is one, specificity is another. So you have to make it big enough to see something, but not too big. And so How do we look at we scan? We have